these lambdas are eigenvalues. And if we kind of look at this, what's going on here, this multiplication right here is a certain weighting for each of these. So the eigenvalue tells me how big how much I'm gonna multiply by each of these eigenvectors. And those eigenvectors kind of make up the columns of A. Q transpose is going to sort of represent the mixture that I make of those components. So I'm thinking of these as the components that make up columns of A, and then Q transpose kind of tells me how to mix them together to make each of the particular columns. But this is going to say, in that mixture, in all of the mixtures looked at the same time, this is the most important component of those columns. Another thing to notice is that this right here gives us a projection into the space spanned by Q1. So we're actually looking at, we can kind of think of this as breaking the transformation of A down into one-dimensional subspaces that are orthogonal to each other, and then we add them together to produce columns of A. Okay. I want to reproduce something like that. I want to reproduce this ability to approximate this big matrix right here, this square matrix, but I want to be able to do it with matrices that are definitely non-square. Okay? I can't do an eigenvector-eigenvalue decomposition. If it's not a square matrix, the concept of eigenvectors and eigenvalues doesn't even make sense anymore, right? If I multiply, so this is an n by m matrix, and I multiply this by an m by 1 matrix, or vector, I can't get something that's a multiple of that n by 1 because I don't even get an n by 1. I get an n by 1. So it's the things that come out at the other side aren't even in the same space, so I can't talk about one being a multiple of the other. But it turns out there is something that we can do. And in many ways, it's even better than this decomposition. And that's called singular value decomposition. This was called the spectral decomposition, and it was decomposition with respect to the spectrum of A. This is the singular value decomposition, and it's very similar to this, but it works for every matrix. No matter what the matrix is, it doesn't have to be square. It doesn't have to be symmetric. It doesn't have to be square. It doesn't have to be all these other things. So the singular value decomposition is going to be written like this: A equals U. Yeah, let's just use U sigma V transpose. And we're again going to have orthonormal here and here. So U and V will be orthonormal. The U's and V's will represent something that's kind of like eigenvectors. And this sigma right here will be diagonal. Now we have to get the dimensions to match up to make sense. So this is going to be an n by n. This is going to be an n by m. They have to be square if they're orthonormal for that to make sense. And the sigma in the middle is an n by m. So it matches the dimension of the original matrix A. This is something like a similarity transformation, right? It's kind of like a similarity transformation in that we're multiplying orthonormal vectors on either side, and what we get after the transformation is a diagonal matrix with the same dimension. Now these U, sigma, and V transpose, you can think of them in very similar ways to what we're thinking about here. So there's some multiplication by an orthonormal matrix that puts us in a different basis. With respect to that basis, the transformation A can be represented just as a diagonal matrix, and then we change basis back to the original basis. Okay. So, how can we compute this thing? Well, if we assume that such a thing exists, then let's look at A transpose A. A transpose A. There we go. So when I use this, let's assume that this decomposition does exist. A transpose will be V sigma U transpose, right? And then A will be U sigma V transpose, right? This is I, so that kind of goes away in the product. And what we get is V sigma squared V transpose. And this we know how to get, because A transpose A is symmetric. And so V is our Q here from the spectral decomposition. Lambda, well, we've got V transpose and Q transpose right here. And we have the diagonal matrix. Well, if sigma is a diagonal matrix, then sigma squared is definitely a diagonal matrix. So if we compute the spectral decomposition of A transpose A, we will get a V, some diagonal matrix V transpose. The problem is, well, there's no problem for getting V. V is going to be the eigenvectors of A transpose A. Sigma squared, on the other hand, might be a little bit of a problem, because if we want to compute sigma from sigma squared, we need to be able to take the square root of every element in this matrix. The lambda that we would get from the spectral decomposition. Right? Which means they all have to be non-negative. How can we demonstrate that? Well, if we look at A transpose A, we want to say that all of the eigenvalues are let me think about this for just a second. We want to say that all the eigenvalues are positive. I prepared something for this, and now it's slipping out of my head. So, if I take A transpose A X, then I should get lambda X. And if I multiply X on this side, X transpose on this side, I should get X transpose lambda X, right? Okay. So this is equal to lambda times X transpose X, which is just the norm of X squared, which is going to be a positive number. And so what I will get over here, this is a positive number exactly whenever lambda is a positive number, right? Okay. So let me rewrite this as AX transpose AX. So this is the dot product of AX with itself, which is the norm of AX squared. And we know the norm of ax squared. Well, this is the sum of squares or whatever, but we also know that the norm is always non-negative. So this is always 0. Which means that lambda is non-negative. Lambda is non-negative. The eigenvalues of this, the entries of sigma squared are non-negative, which means that we can just take the square root of the eigenvalues of A transpose A. So if we call these lambda 1 up to lambda r, so that'll be the rank of the A transpose A, which will be however many non-zero eigenvalues there are. Then we'll write sigma as square root of lambda 1, square root of lambda 2, all the way down to square root of lambda r. And then we might have some zeros. Okay? And then everything else is 0. So we'll think of this as just being the non-zero entries will be right here. And just like we did before, we'll order them in decreasing magnitude. In fact, now we can order them according to lesser than, as opposed to smaller than, because they're all positive. So that's the same, they mean the same thing. So that's how we'll compute sigma. So we'll call these entries sigma 1, sigma 2, and sigma r, however many non-zeros we have, and then possibly, okay, let's do it like this. There's a block here and a block here, and outside of that block, they're all blocks of zeros. So these are called singular values. These are the eigenvectors. Well, I kind of already said these were the eigenvectors of A transpose A. But in this context, we don't want to talk about what they are with respect to A transpose A. We want to give them a name with respect to A. And so these are called bits, and I should put it over here. Right. Singular vectors. And these are drawing all kinds of arrows here. So those are the singular values. Now we just need to compute U. So we've done this nice transformation here. So we've gotten A equals something times sigma U transpose. This product right here is probably not A. We need to figure out something that we can multiply here. The book does this in a different way. I'm going to do this a different way from what the book does. So instead of looking at A transpose A, I'm going to look at A transpose. I should go back here and say that this is A transpose A is n by n? No. This is n by m, so it's A transpose A is an n by m matrix. A transpose is an n by n matrix. And if we do the same multiplication here, we get A is U sigma U transpose. And A transpose is V sigma U transpose. You gonna make it? You look very tired. There's almost over. That's I again. This is sigma squared, and we get U sigma squared, U transpose. We have a little bit of a problem. So this A transpose A is going to have M eigenvalues counting multiplicity. A transpose A is going to have N eigenvalues counting multiplicity. I'm not going to go into the details of this today, but these will have the same eigenvalues, the same non-zero eigenvalues. The difference, the way it's going to make up the difference between those two numbers of eigenvalues is going to be with zeros. So these two matrices have the same rank. They have the same number of non-zero eigenvalues. Okay, so we do this, and then we do the spectral decomposition in the same way, and that gives us the eigenvectors of A transpose. And so we get with respect to A, we call these the left singular vectors. There are other ways to compute U. U doesn't necessarily have to be, so this is just one way to compute them. Let me just really quickly say why you might not want to compute it this way. From a computational point of view, when we were looking at something like this, we were thinking, well, maybe this is like a 1 megapixel picture. So it has 1 million entries going down and then like only 100 going across, right? So A transpose A was a 100 by 100 matrix. N by N would have been a 1,000,000 by 1,000,000 matrix. So there's a good reason to skip that. The book gives you an explanation of how you can compute U without doing it this way. So we can actually just, based on what A is, we can figure out what this should be. It actually turns out to be a matrix that's A times V, and then we can just fill it in with whatever we want after that to make it a N by N matrix. Because all we really need is an orthonormal matrix here, an orthonormal matrix, an orthonormal matrix here, an orthonormal matrix here, and a diagonal matrix or block diagonal. So it's diagonal, but part of it is just all zeros. Now, it doesn't really matter which way we do it, and in fact, those other vectors after the first bar vectors that you would get are the first vectors that you would get from A to B right here. The rest of them don't matter because of what happens when you expand this out. So when you multiply this U, which we'll call U1 up to U, and V we'll call V1 up to VU. Whenever you do this multiplication out, I'm just going to keep going, and feel free to leave. This is all optional, right? When we do this multiplication, we're only going to get our non-zero values here. So when we do U sigma V transpose, this is going to be equal to U1 sigma 1 V1 transpose, right? Plus U2, I should write the constant out in front, or the scalar out in front. Sigma 2 U2 V2 transpose plus I. Eventually you're going to get to the last singular value. You're going to get to the last non-zero value in the sigma. Sigma R, UR, VR transpose, and then the rest of these will be zero. So after the first R components of this, the first R vectors in U or the first R rows in V transpose, it's not going to matter what they are. So we can just do something like this where we compute the first so many and then just fill it in with an orthonormal columns to get the complete U. So that's the way it's often done in practice. Now, what do we see? Before, when we had this, the spectral decomposition, we could use this to approximate this matrix A. Now what we have is this matrix A. We don't think of this as representing a linear transformation anymore. We could think of it as if we multiply it by a basis vector. So 0, 1, 0, 0, 0, 0, right? Second basis vector. What does this transformation do to this vector? It turns it into the second column of this. So it's sort of like a way of selecting out each data column. If you look at it with respect to this, and then maybe this column tells you how to like mix these together to get something else. But ultimately, we're thinking about this just as data. It's just a square block that stores some data. Well, because of all of this matrix multiplication, which has a connection with linear transformations, right? That's one way of looking at the same thing. We come to this conclusion at the end, which is that this collection of data, this just blob of data, well, it's not a blob, it's a rectangle. This rectangle of data can be written as this, plus this, and so on. Now this is a rank 1 matrix. And this rank 1 matrix is as close a rank 1 matrix can possibly be to this data. We've taken just a big block of arbitrary data, and we figured out how to compress it down to a much smaller piece of data. Right? One that approximates this, and this, I'm not going to prove this because this is a much more difficult theorem. This is the best rank 1 approximation possible to that data. Similarly, this is the best rank 2 approximation, and when we get it all the way up to R, we have the exact A. And this also tells us that A must be whatever the last zero singular value that we have. That's what the rank has to be. So A has to be a rank R matrix. Okay. Now, just in the same way that we said that these were the components that make up the things that are in A, and this is how important each of the components is, and we've ranked them according to importance. We've done the same thing over here. And now if we go back and we look at the face, in the face example, this is the most striking because it's something you can really look at. You take this big collection of faces, very careful to center them all so they're all in the same appropriate place, right? And then you go over here and you perform your singular value decomposition, and now you have a U1, U2, up to U, let's just say we only go to UR, right? And then we don't care about the rest. Okay. These, now we can pull one of these out and then turn it back into something. And lo and behold, what do we find? We find that this most important piece right here, in fact, is a face. And it's a face that somehow captures all of the variation in all of the faces here. It's something that you will recognize immediately as a face. When you leave here, Google the term eigenfaces. Somehow this eigenface will represent the main way in which faces vary in the data set. As we go from multiplying this right here. No, that's not what I want. This represents a subspace in the R1 million, the 1 million dimensional real vector space in which these faces live. This represents a subspace in which the most variation happens. Right? This one will represent the subspace orthogonal to the first space in which the most variation happens in the faces, and so on. So what we've really done is we've taken the data, not only what we get out, this is a way that we can compress the data, approximate it in with something much smaller than the data itself. But we also get an understanding of the data out of this. This somehow represents an important feature in the data, important features in the face. Okay. So that's singular value decomposition, and that's what it allows you to do with just linear algebra on arbitrary data. Principal component analysis is just a small step away from this. We do basically the exact same thing, except instead of doing just arbitrary data, what we do is we take all of these data, that was right, and we average all the columns together and then subtract that from each column. So what we've done is we've taken the data and we've centered it, we've taken the mean and we put that at the center. So the mean of all of this data is 0 at the origin, right? So if we think about this in a two-dimensional space, we have data maybe kind of distributed like this, and it kind of is sort of an ellipse, sort of like a normal distribution. It's centered at the origin. And when we compute this A transpose A, with mean-centered data, what you end up getting is, well, you have to scale it appropriately, but what you get after you scale it is called the covariance matrix. So it tells us how each of the particular variables in the data, how they vary with each other. If one gets larger and the other one gets larger at the same time, then you'll have a big entry in the covariance matrix. And if there's no relationship between how this one gets bigger or smaller and this one gets bigger or smaller, then the entry in the covariance matrix will be 0. And what you get at the end of this is a transformation where you're looking at orthogonal directions in the space. So all of the columns of U are orthogonal. And the sigma represents that once you apply that change of variables, that transformation, what do we call this? Change of basis. Once you apply that change of basis, in that space there's no correlation between the variables, which means all of the variance is within each component. So, and this is not a good example because, so, something like this, right? Because we have the first entry, so the first, we have no covariance, and we have in the first direction the largest possible variance. What we get is that our first left singular vector will point in this direction. And then we get something that's orthogonal to it that points in the direction of maximum variance, which is in this direction. And this gives us sort of like, with our arbitrary data, a way of sort of immediately testing how it fits into the variance of all of the other data that we have in the data set. So anyway, that's principal component analysis. And the most common application of this in practice is to take something that's very high dimension, like 1 million, and reduce it down to something very small. So if we were looking at faces, what we end up with at the end is, let's say we only take the first 3 principal components. We have a way of representing faces in a 3-dimensional space. So every single one of the faces in our data set can now be represented by just 3 numbers. And we see all of the variation among the data set just by varying these 3 numbers. Okay, I'll stop there.
Thank you. That was very interesting. Have a good weekend.
You too.